Welcome to this training video on the ReCAP LVR DCP design software. The production of this video was supported by UK aid through the Research for Community Access Partnership ReCAP. The video was produced by Infra-Africa Consultants Botswana as part of a suite of tools aimed at facilitating the cost-effective and environmentally optimized design of low-volume roads in both tropical and subtropical regions of the world. By way of background, UK aid through the Foreign, Commonwealth and Development Office has been at the forefront of supporting research in the design of low-volume roads in Africa and Asia to improve access to infrastructure and transport services. Such access is, of course, essential to economic growth and service delivery in all developing countries where low-volume roads provide the main form of transport in rural areas. ReCAP has been working closely with partner governments in Africa and Asia and has produced technical documentation that reflects best practice, including a manual on pavement design of low-volume roads using the DCP-DN method. As part of the suite of tools on the use of the DCP-DN design method, the ReCAP LVR DCP software has also been produced to assist engineers in the design of low-volume roads. Like any software package, the ReCAP LVR DCP software should be viewed only as a tool to assist in the design process. To be able to use the design software effectively, the key concepts and principles of the DCP-DN Pavement Design Method must be fully understood by the designer as a basis for applying sound engineering judgment and to be able to produce appropriate and cost-effective designs. It is therefore crucial that designers should carefully study the contents of the DCP-DN Pavement Design Manual before attempting to use the software. The main purpose of the software is to provide users with a relatively easy-to-use tool with an intuitive user interface that facilitates the undertaking of all the procedures required to properly design a low-volume road. The objective is to ensure that the software is correctly applied to support the design approach embodied in the DCP-DN Pavement Design Manual. The software also includes a user manual that guides users in a step-by-step manner in all the procedures required to undertake the complete design of both paved and unpaved low-volume roads. The video provides detailed step-by-step guidance through illustrated examples of all the procedures required to produce an optimized low-volume road design from start to finish. In other words, from creating a field project to entering and analyzing laboratory DN test data. Let's now look briefly at how we can download the software, install it, and fix any software problems that users may experience. Downloading the software is fairly easy. The user just goes to the CSRA website where the software is housed. It's then simply a matter of selecting the low-volume roads DCP software from the menu, filling in an online registration form to get free access to the software download page, and then downloading the software installation file to your computer. Installing the software is also quite straightforward. The user simply locates the installation file on his or her computer, clicks on the file, and follows the instructions on screen. When the installation is complete, the user simply clicks Finish. The shortcut icon will now appear on your desktop, and you are ready to start using the program. Some users may experience problems in installing the software by way of a DCP execution system error message that a file is missing or is corrupt. This is most likely because your computer system is not quite up to date. To fix this problem, the user will need to search for the missing file or error code on the internet. We have provided some useful internet sites that will help you to find the missing file. You should make sure that the files that you install are compatible with your computer system, which may be 32-bit or 64-bit. You then just follow the instructions on screen to solve your particular problem. If you are still not successful, then you can also go onto this user forum website, which is hosted by CSIR, where you may find a solution to a problem raised by other users. If that is not helpful, then you will need to seek IT support.
The video comprises 4 training modules, with a total duration of about 38 minutes. Each module is self-standing and can be viewed separately and repeatedly until the user have grasped all the aspects in that module. For the best learning outcome, new users of the software are advised to view one module at a time and then to emulate the process on their own computers before proceeding to the next one. In this module, we'll show how to create new field projects and various methods for entering DCP test point data. To get started, you must create a project. So click on the desktop icon, and from the opening screen, select Create a new project. And then you must select for field project. Click OK. Then you must define the location of the project. Let's say Eastern region. Let's say the road number is D123. Then you must select the project date. And let's say that you carried out the DCP survey on Friday the 2nd of October. Then you have to save the file before you can proceed. So click on this button and type in the file name. And save it. Then you can proceed by clicking OK. Before we start entering DCP test point data, let's just look at the menu. It's basically a standard Windows menu that you are used to from other software, but there's a couple of options that we need to explain. The Insert allows you to insert a new DCP test point. The Analysis menu is not activated until we actually entered DCP data. The Sections menu will only be used once we get around to the pavement design process. From the System menu, you can adjust your DCP system settings. If you are using the standard design option as recommended in the DCP-DN Pavement Design Manual, you leave this box open. If you are using the Percentiles option, you tick this box. For all other settings, it is recommended that you leave them as they are. Under Traffic Load Class Design Curves configuration, you will find all the predefined design curves. For paved roads with a prefix of TLC, and for gravel roads with a prefix of HVPD. The paved road traffic load classes are defined in terms of million equivalent standard axles, and the gravel road traffic load design classes are defined in terms of number of heavy vehicles per day. For advanced users and experienced designers, it is also possible to define new design curves by using the user-defined options, whereby you can enter a new pavement structure and corresponding DN values, as explained in the DCP-DN Pavement Design Manual. Under Report Options, you can define what to include in your reports once you get around to printing them, but it's recommended to leave all the boxes ticked. If you need help, you can access the user manual by clicking Help Topics and navigate to the table of contents if it's not already displayed. Search for the item that you need help on. Click on it. And when you read up on that, you can navigate back to the table of contents by clicking on the numbered heading. In addition to the menu, there are also shortcut icons that can be used. These are the standard Windows ones that you are used to. This one will allow you to insert a new DCP test point. And these two will allow you to do DCP test point analysis for a single point or multiple points respectively. Now you're ready to start entering DCP test point data. And you can insert a new point by clicking this shortcut icon. The numbering of the points is done automatically in ascending order as you enter new points. You can also rename the points later if you wish to. First, you have to enter the chainage for the point, and let's say we started at kilometer 0, we can leave that unchanged. Then you have to enter the road width at that point. Let's say it was 5 meters wide. Then you have to define the position on the road for that test point. If it was on the center line, you leave this as 0.0. If it was to one side, you enter the distance from the center line, say 2.4 meter. And then you have to define the side, whether it's left-hand side or right-hand side. So let's say it's left-hand side. The survey date is already set as the project date, but if you conducted the DCP survey over more than 1 day, you can change the date here. The road condition is merely a descriptive field and it doesn't affect your design. You can choose one of these predefined options, severe, warning or sound, or you can refer to the notes field where you can record what you observed at that test point. And let's say standing water in left-hand side drain. This will serve as a reminder for why the pavement was so weak at that point for later reference. The next step is to record the number of blows per reading. The default number is 5, but this number can be adjusted up or down depending on what you actually applied on site. Very often you will find that on site you need to reduce the number of blows as you get down into softer layers. In that case, you need to tick for variable blows. The number of layers is fixed to the 5 layers as per the DCP-DN catalog. Then you have to select the TLC design curve for the road you are designing as per your traffic estimate. And let's say you arrive at TLC 0.3. Now you are ready to start recording the DCP data. And you click on this tab and you start entering the readings. The first reading you record is the 0 reading where you have just seated the cone as per the instructions in the DCP-DN manual. So let's say that was 78 millimeter. You hit the tab key, record the next reading, 111, hit the tab, 123, hit the tab key, 145, and so on. Let's say the last 2 readings you record are 790 and 859. At this point, you have not yet reached 800 millimeter penetration depth because the last reading has to be 800 plus the first reading, 78. And if you try to proceed from this point by inserting a new point, you will get an error message to manually enter additional data readings or extrapolate using the last 2 data readings. Normally it's okay to choose extrapolate and click OK. When you enter DCP readings, you need to ensure that they are entered correctly. And let's say that on reading number 11, you recorded 223 instead of 323. Then what happens if you try to proceed by, for instance, inserting a new test point? You get the error message that the DCP readings are in non-ascending order. You click OK, and you will see that this line is now disabled. So delete that row by pressing the delete row button. And then insert a blank row to enter the correct reading, 323. You may also have forgotten to record the correct reading number 11. In this case, just insert a blank row and then record the correct reading, 323. Instead of typing in the data directly in the software, you can import the data from an Excel spreadsheet. In the case of fixed blows per reading, this number must be set to the same number that you have recorded on your field form. First, copy the data in Excel. Then back in the software, you just press the paste button at the bottom of the page. In the case of variable blows per reading, you must first tick this box. Then in Excel, you need to copy the columns both for the readings and the blows per reading. Then back in the program, again, you just paste. If you want to insert an intermediate test point, say in between test 6 and 7, you just click on New Test Point. You record the change for the new test, 1.075. Then you copy the data from the Excel spreadsheet, as we shown before. And back in the software, you just paste them in. Now it's recorded as test number 34, but you can rename it. Call it test number 6A. Click OK. Then you can order the test points by name, and it will jump up to the correct place. This module will show you how to analyze single and multiple DCP test points. For each test point, you can quickly analyze the data to see if you got sufficient strength compared to the catalog requirements. Click on the single analysis icon, select your point, and click OK. The analysis output window shows 3 different diagrams at the bottom, each of which can be enlarged for a better view. In the layer strength diagram, the thick red line shows the weighted average in situ DN values per layer, and the dashed blue line shows the catalog values for the selected traffic load class. The diagram thus shows that the top layer is too weak, the second and third layers are just strong enough, and the 2 bottom layers have some excess strength compared to the catalog requirements. The DCP balance curve diagram shows that we have a well-balanced deep structure at this point. The balance curve for the point is closely following one of these standard pavement balance curves. This means that we have a smooth decrease in strength with depth in the pavement. For a full explanation of the balance concept, which is a unique feature of the DCP-DN method, refer to the DCP-DN Pavement Design Manual. It is also useful to look at the normalized and redefined layers. In this layer strength diagram, the thick red line indicates the weighted average DN for the layers that the DCP has actually detected. So we see that at this point, the DCP detected only 3 layers that are statistically different. If there were any weak interlayers in the pavement structure that would not be detected by looking at the standard layer strength diagram, it will show up on this diagram. The analysis window also shows the DSN 800 value at that point, and the DSN 450, and the ratio between those 2 values. And we see that at this point, the upper 450 mm of the pavement contributes 72% to the overall bearing capacity at that point. We can further see the weighted average DN values per layer, the number of blows to penetrate each layer, and the standard deviation of the DN values within each layer. In a similar fashion, you can analyze multiple points. Click on the multiple point analysis button, and from this screen you can select the points you want to analyze. You select points by way of these buttons, either one point at a time or all the points, and deselect points either one point at a time or all the points. Now let's say that we want to analyze all the points apart from the ones on the center line, which tend to be stronger than the ones towards the edge of the road. So select all the points, then deselect all the points at the center line. Then you select the design curve, which is TLC 0.3. Then you can give the analysis a name. You can save it as left-hand side and right-hand side. Click OK, and then click OK to run the analysis. The output is similar to the one for single analysis, and we can see here that the three uppermost layers have insufficient strength compared to the DCP-DN catalog. We have now come to the module where we will show you step by step how to undertake a pavement design. To start the design process, you have to go to the sections menu. And the first thing you have to do is to calculate all the properties, the DSN 450, DSN 800 and the DNs. Select your design curve, which is TLC 0.3, click OK. You now get the message that the road project is now set as one DCP section. From this screen, you can easily identify outliers, that is, points that are either very weak or very strong, and you may want to exclude those points from further analysis. Next, you can validate your DCP test point data, and this function will give you a graphical representation of all the test points. This screen displays the position of all the test points on the road, but you can also look at the number of layers that the DCP actually detected. The last option on this menu will give you a view of the redefined layers seen from top down. The next step is to determine uniform sections. And you can see that the whole road is initially set as one section. You can select which of the curves to display, and normally the DSN 450 and the Q-sum curve for the three top layers are the most important, so we can deselect DSN 800. These spikes in the curves are caused by outliers which tend to distort your weighted average calculations. So therefore we can go back and eliminate them before we proceed. And we can see that point number 11 has an abnormally high DSN 450 value. By right-clicking, I can mark that point as invalid. In the same manner, I've marked another 4 points as invalid. And if we now look at the curves again, we can see that we have now got a much clearer picture on which to determine our uniform sections. The uniform section start and end points are where the curves change their general direction, and we can see that the curve for the DSN 450 changes direction from gently rising to falling at this chainage, and that coincides with the same changing direction for the three top layers. So by right-clicking at this point, you can add a section by clicking and then clicking again. And you ask whether you want to add a section there, click yes, and the section delimiter automatically snaps to the nearest DCP test point. Going further, we can see that the same occurs at this chainage. We add a section here, click yes. Now we have three sections for this road. These section delimiters can be changed or adjusted by dragging them to different positions. or can be deleted. In this manner, you can experiment with different sections to see how that affects your design. When you have identified the outlier points, for instance this one with a very low DSN 450 value, and you can see also very high DN values for the top 3 layers, you may want to go back in the field to investigate the cause of the problem, and perhaps also make additional tests around that point to investigate the extent of the problem. Very often these low values are caused by inadequate drainage at those points. High DSN values may be caused by rocky ground at those points and are usually not a big problem. When you have determined the uniform sections, you can get to the DCP sections report via the menu or by clicking on this tab. The DCP sections report shows 3 different tables, which are all identical initially. The first table shows the weighted averages for the DN values for all layers and all sections. In the second table, we are later going to enter the DN values corrected for moisture and density. And the third table will show us the final pavement design after we have decided how many layers to add for each section. The design requirements for the selected traffic load class is shown in this column, and the numbers in brackets indicate the range within which we can normally improve the layer, for instance by ripping and recompacting. The color coding is explained underneath the tables. Pink color means that the layer has inadequate strength compared to the catalog requirement. Orange means that it's marginally compliant, and green means that it's fully compliant with the requirements. To determine the adjusted DN values to be used for the design, the following must be borne in mind. All the factors that influence the performance of the pavement in the long term must be taken into account for making sound engineering judgments. Uniform sections must be designed separately based on the particular conditions within the sections to achieve an environmentally optimized design. And drainage is the most important aspect of the design of low-volume roads, and particular emphasis must be put on achieving adequate drainage after upgrading to ensure that the pavement is kept as dry as possible in service. For the drainage requirements, refer to the DCP-DN Pavement Design Manual. In this example, we're assuming that the DCP survey was carried out in the wet season, when the pavement was in its weakest condition. Thus, we assume that the moisture content in the 3 lower layers will remain more or less the same in the long term. We therefore do not enter adjusted DN values for the 3 lower layers. For the 2 upper layers, we have determined through the laboratory DN test the appropriate adjusted DN values on which to base the design, which we then enter in the appropriate cells. In the first section, the adjusted DN values were 5.9 in the top layer and 7.1 in the second layer. In the middle section, there were only minor adjustments, 9.0 in the top layer and 11 in the second layer. In the third section, it was 3.5 in the top layer and 6.3 in the second layer. By comparing the adjusted DN values in the middle table with the design requirements for the selected traffic load class, we can then determine how many layers we need to add for each section. So let's add 1 layer for section 1. The software then pushes down the in-situ layers in steps corresponding to the number of layers we have added. And it leaves an empty cell for entering a laboratory DN value for the bore pit material that we are going to use. In section 2, let's try with 2 layers. The same thing happens, and we have now got empty cells for entering laboratory DN values for a new base layer and a new subbase layer. In section 3, the adjusted DN value is not far off from the design requirement of 3.2 mm per blow. So we may try to improve that layer by compacting it to refusal or by blending it with better material. If we choose the blending option, we have to test the blended material in the laboratory. And let's assume that we achieved the lab DN value of 3.2 mm per blow. We can then enter that value in the middle table. And then we can see that we don't have to construct a new base layer in the third section. As a last step, we can now enter the laboratory DN values for the base layer material and for the subbase material. This will then be your final design for that road. You can then analyze the sections by choosing the DCP section analysis per section option, and you can analyze the existing structure before you applied your design or the upgraded structure. So let's just analyze section 1, upgraded structure. And this shows that all the layers are now in compliance with the design requirements, and we have got a well-balanced deep structure. We also see that we have met the DSN 800 requirement and that we have a ratio of DSN 450 to the DSN 800 of 79%. You can then print a report for the sections that you have just analyzed by choosing the detailed report, which goes over 3 pages, or a summary report over 1 page. For an existing gravel road which is in fairly good shape and where the moisture content in the in situ pavement layers is deemed to be fairly uniform, it may be feasible to use the Percentiles option for design. And you can select that under the DCP system settings. We'll tick this box, click OK, and the software now displays all the weighted average DN values, defaulting to the 50th percentile for all the sections and the layers. You have to go through the same thought process as in the previous example and select your percentiles based on whether you think the long-term EMC in the pavement will be higher, equal to, or lower than the moisture content at the time of the DCP survey. In that assessment, you also have to factor in that the drainage conditions normally will be improved after upgrading. In each cell in the middle table, you can then select the appropriate percentile value to be used for design. So let's again assume that the DCP survey was carried out in the wet season and that the long-term equilibrium moisture content in the 3 bottom layers will not change in the long term. We further assume that the top 2 layers in sections 1 and 3 will become drier than at the time of the DCP survey, while the equilibrium moisture content in the top 2 layers in section 2 will remain as it was at the time of the DCP survey. This means that the top 2 layers in sections 1 and 3 will be stronger in the long term, and that we can select a lower DN value to be used for design for those layers. Normally, the 20th percentile DN value would be appropriate. So we select the 20th percentile for the top two layers in sections 1 and 3. And having done that, we can now consider how many layers we need to add for each section. So let's consider the design section by section. Let's start by adding one layer in section 1. From this we see that the in situ top layer, which has now become the subbase, is still outside the design requirements as per the DCP-DN catalog. But the margin is very small, and there could be scope for improving the layer before we put the base layer on top. In section 2, let's add 2 layers, and that seems to be fine. We just have to add a base layer and a subbase layer with the appropriate specifications. In section 3, let's add 1 layer, and that's also fine. We just have to add a base layer with the appropriate specifications. So the only problem remaining now is the improvement of the in situ top layer in section 1, which we can probably solve by mechanically stabilizing this layer to meet the specifications for the subbase. For the design of gravel roads, it's important to note that the pavement design process shown in this module is exactly the same for both paved roads and gravel roads. The additional important aspect of gravel road design, which is not covered in the module, is the selection of gravel wearing course material. For best performance of gravel roads, it is important that the selection of gravel wearing course material is done according to the specifications in the DCP Pavement Design Manual. The last module explains how to create a laboratory project and how to record and analyze laboratory test data. To create a laboratory project, you open the software, select Create a new project, and select Laboratory, and click OK. Then you have to assign a job reference number or descriptor to make sure that you don't mix it up with other laboratory test results. And say you can use your road number, D123. And if it is test pit results you're going to record, you can include that in the job reference. Then you have to save the file with a unique name and proceed. The menu in the laboratory module is similar to the one for the field projects with some minor differences. Under Insert, you can insert a new mode for testing. The Analysis menu is not activated until you've entered test results. From the Systems menu, you can define your report options, but it's recommended to leave them as they are. You can also insert a new mode by clicking on this icon. Now we can insert a new mode for testing. And we have to define the sample number, the mold number. OK. We assign a test bit number. And then we have to specify the thickness of the layer from which we took the sample by defining the lower and upper layer boundaries. And say the lower boundary was 300 and the upper boundary was 150. Click OK. Then we have to define the depth of the sample in the CBR mold. And you can click on this icon to get an explanation of what we mean by the depth of the sample. So let's define the depth of the sample as 120 millimeter. The variable blows option is pre-selected for the laboratory DN test. Then we have to define the design DN value for the material that we are testing. And can click on this button. That brings up the DCP-DN catalog. If you're testing material for a base layer for TLC 0.3, you can then enter the base layer requirement, 3.2 millimeter per blow. Click OK. Then you can also enter the OMC for that material, say 6.7%. Then you have to define at what compactive effort you are going to perform the test. You can choose between 3 compactive efforts. Say this one is at heavy compaction. Then you have to select the moisture content for that sample. It can be soaked OMC or 0.75 OMC. So let's say this one is at OMC. Then you are ready to start entering the DCP readings and the number of blows per reading. It is easiest to take the laptop with you into the lab and record the readings straight into the software. When you get towards the bottom of the mold, you should reduce the number of blows to make sure that the cone does not hit the base plate and get blunted. You can prevent that by checking the depth of the penetration, which is the difference between the last reading and the zero reading. And when that difference approaches the depth of the sample, you must be careful. So the last reading you record on this test is at one blow, you have reached 256 millimeter. But at this point, you have not yet reached the full depth of the sample. And if you now try to insert a new mold, you are told to manually enter additional data readings or to extrapolate. So click extrapolate and OK. Now you can analyze that mold. And this diagram shows that the material does not quite meet the requirements for the base layer. The software calculates a best fit value in the middle portion of the mold, excluding the top 15 and bottom 15 millimeter. And the best fit value is given above the diagram at 3.9 millimeter per blow. In a similar fashion, you can analyze multiple molds by clicking this icon. And from this screen, you can select which molds to analyze. And you maneuver between the panels by way of these arrows. The important thing is that you analyze together only molds compacted at the same compactive effort and at the same moisture content. And when you're done selecting your molds, click OK, you get the result. The analysis window also gives you the weighted average DN in millimeter per blow for the whole depth of the mold, which you can see is different from the best fit value. That is because the penetration rate in the upper 15 millimeter, as well as in the bottom 15 millimeter, tends to be different from the rate in the middle portion of the mold. You can then print the report on your analysis results, either a detailed report, which goes over 3 pages, or a summary report over 1 page. For recording of test results for borrow pit materials, it's advisable to open up a separate file so as not to mix them up with the results from test pits on the road. And you can give a job reference number with the road number plus the borrow pits. Save it. Proceed. Then when you enter a new mold, you again have to enter the sample number. Let's say 2, 2. And now you have to identify whether the sample was taken from a stockpile or from a test pit within the borrow pit. Say it was from a stockpile. Record the borrow pit number, say 3. A stockpile number, if you have more than one stockpile, could be 2. And then the location, say top center. Okay. For the rest, everything is similar to the previous example.
As would be apparent from the contents of this video, the ReCAP LVR DCP software provides users with a versatile, flexible, and user-friendly tool for undertaking the environmentally optimized design of a low-volume road. The video provides step-by-step guidance through illustrated examples of all the procedures required to undertake the design of both paved and unpaved low-volume roads. Users should be able to use the software confidently and in an informed manner to create field projects, enter and analyze DCP test point data, and undertake a pavement design as described in the DCP-DN Pavement Design Manual. As emphasized throughout this video, it is crucial that designers are intimately familiar with the contents of the DCP-DN Pavement Design Manual. In addition, they need to be involved with the DCP data collection on-site so that they can interpret and use this data in an informed manner during the design process. It is also worth emphasizing that the design of a low-volume road requires a hands-on approach from start to finish. Thus, the designer is forced to think through each step in the design process to make realistic assumptions and engineering judgments to produce optimized designs at minimum life cycle cost. One of the goals of ReCAP is to improve accessibility of the rural poor in Africa and Asia to economic opportunities and social facilities through improvements to road infrastructure and transport services. The attainment of this goal presents a multidimensional challenge that goes beyond the design aspects of a low-volume road. Thus, one could say that the successful engineering of a low-volume road requires ingenuity, imagination, and innovation. It entails working with nature and using locally available, non-standard materials and other resources in an optimal and environmentally sustainable manner. It will rely on planning, design, construction, and maintenance techniques that maximize involvement of local communities and contractors. When properly engineered to an appropriate standard, a low-volume road will provide sustainable access to the rural poor in African and Asian countries through improvements to road infrastructure, leading to economic growth, development, and a reduction in poverty. Finally, the production team wishes to acknowledge the invaluable support and facilitation provided for the production of this training video by the ReCAP Deputy Team Leader and Infrastructure Research Manager, Engineer Nkululeko Letta. The production and narration of the video were undertaken by Mike Pinnard and Yon Hongwei.